So can I have a confirmation that you can listen to me? Sergio, for button here? Okay, thanks. Sergio, mir dugan? Show me. Okay, so let's continue where we left. And it looks like these numbers, or these complex numbers that we have written here, they can be represented using the polar representation as Ri theta as square root of 5 e to the power I 27. Let me write this one 27. And here we have square root of 13 e to the power I minus 34. I'm rounding them. And here we get this is equal to square root of 5 e to the power I minus 27 again. Okay, so now the moment these complex numbers they are written in the polar representation, we can argue that they look slightly better. Now, at this time, let's do another exercise here. But now, in this section, we are going to see a little more in detail the relationship between the complex numbers and the matrix algebra, or the linear algebra. And as an example, let's start with a matrix which is defined as in here. So our matrix is A, which is equal to 1, 1, 1, 1, minus 1, 0. And we have a vector which is x0 equal to, so if you give me a pair of numbers, any pair of numbers, so let's pick 2, 1. Let's give a number, an x0 equal to 2, 1. 2, 1, if we are to draw it, this is what we get. This is the vector x0. And then the question is, what do we obtain if we multiply A with x0? So here we have 1, 1, minus 1, 0, multiplied by 2, 1. What do we get here? We get here 3 minus 2. Where is 3 minus 2 here in this graph? This is 3. This is minus 1, minus 2. Okay, so this is AX0. Okay, and then we multiply again 1, 1, minus 1, 0. We multiply with 3 minus 2. And here we get what? This is like 1. 1 minus 3. So this is 1. I'll continue here. This is minus 3. So this is a squared times x0. So what we are doing right here, we are simply rotating the initial vector. This is 1, 1, minus 1, 0. And we multiply here 1 minus 3. And here we get minus 2, minus 1. So minus 2, minus 1, it is minus 1, minus 2. So this is a cubed times x0. We continue again. Minus 2, minus 1. And this would be equal to minus 3, 2. Minus 3, 2. It's here and here. So this is minus 3, 2, and we can write this one as a to the power 4 times x0. So if we multiply this again, we get minus 1 and 3. Minus 1 and 3, it is we get this. And finally, if we get 2, 1. So then finally we get 2, 1, which is this initial vector. So this one is also equal a to the power 6 times a0. So looking at this example, can you find what is a to the power 29 times x0? What is this? Shachet, can you answer this?
I just came from the break and I didn't follow this exercise.
Okay, so let me explain what we did here, Shachet. So we started with the matrix A, which is given here. And we also gave an initial vector x0, which is 2, 1. So 2, 1, this is where we have it, so we can easily see is this vector. Then we multiply the 2, 1 with this matrix, we got 3 minus 2, right? So we started with this one, and A times x0, it is this 3 minus 2, okay? We multiply again by A, we apply this matrix A onto the vector 3 minus 2, we get 1 minus 3, so we got this other vector, which is a squared x0. We multiply again, we get a cubed x0, is this vector, multiplied by another A. So it looks like we are continuously rotating, okay? And then, so a to the power 6 times x0, we come to the same initial vector. So my question is, what do we get if we multiply a to the power 29 times x0?
A0?
Times x0. x0 is this, it was this initial vector.
Yes, I think that...
So a to the power 6 is equal to the identity matrix, okay? Because you can see from here, that a to the power 6 times x0, this is what we get, okay? So what is a to the power 12?
I think that it will be in the second quadrant.
Well, no, it's going to be the same vector. Anfushit jasht, chabon, ti fillon nga x0, kthehesh aty ku ishin fillim. Edhe anfushit të 12, I bën xhiro këtej, kthehesh pa aty ku nise, dakor? Anfushit 18 je pa aty. Pra, shumfishat e gjashtës, ty të kthejnë këtu. Atëherë ty të intereson, what is 29 mod 6? This 29 is equal to 6 times 4 plus 5, which means that a to the power 29 times x0, this is equal to a to the power 24 times a to the power 5 times x0. This one is the identity matrix, so this is a5 times x0. a5 times x0 is right here. So you're right, actually, it's on the second quadrant. I didn't see this one. So this would be the answer. But now, what we can observe here also is that this so it looks like a to the power 6 is equal to the identity matrix, because as you said, it comes back to the initial vector, and a to the power 3 is equal to the minus identity matrix. Because we can see that from here, you rotate 1, 2, 3, this is the negative of this one. From this vector, you rotate 1, 2, 3, you get the negative of this vector. Similarly, the negative of this one we obtain by multiplying 3 times by a. So we can simply say that a to the power 3 is equal to minus 1, 0, 0, minus 1. okay? And a to the power 6 is equal to 1, 0, 0, 1, which is the identity matrix. Now, it looks like what if we try to think now in terms of the multiplication by a complex number. We said that if we multiply by a complex number, what we obtain a rotation of the vectors that we have initially given. So on average, what is the rotational angle by the matrix A? Now, a to the power 6, this is equivalent to a rotation by 360 degrees, okay? This means that the matrix A, it generally, on average, it rotates by an angle 360 by 6, okay? So this is what the matrix A rotates. Now, at the same time, we can look at the following, at the same problem this way. What are, let's try to find, what are the eigenvalues of the matrix A? How can we find those? Someone wants to solve this with me? Who's opening the door? We want to solve to find the eigenvalues of the given matrix A. Someone else? Not Anissa? Someone else from the class? Alisa, okay, we can ask, Alisa, you can answer. So Alisa, what should we do here?
Okay, we first find the determinant, and then should be equal to 0. So it's
we find the determinant of this matrix, right?
yeah. So then we do 1 minus lambda times minus lambda minus plus 1 should be equal to 0.
And then what is lambda?
Lambda is going to be minus beta minus 1 plus the square root of b squared minus 4ac minus 4, 1, 1.
Minus
4, yeah.
Divided by?
2a, so 2.
And this is equal to 1 over 2 plus minus the square root of minus 3 divided by 2. Okay? So, what is the square root of minus 3?
The square root of minus 3 is going to be the square root of 3 times the square root of minus 1. So it's going to be the square root of 3 times I.
That's correct. Okay.
Yeah.
So this is what we obtained. Now, so it looks like lambda 1 is going to be equal to 1 over 2 plus I times square root of 3 over 2. Now, if we have a look at this expression, which angle has a cosine equal to 1 over 2?
60 degrees.
60 degrees, that's true. Which angle has a sine square root of 3 over 2?
60 degrees.
60 degrees. So we can say that here, we can write this one as if this is cosine 60 plus I times sine 60. Would you agree with this, Alisa? I'm asking about this expression here.
Yes.
That's true, okay. So it looks like this lambda, we can simply write this one because this is cosine 60 plus I times sine 60. So, which is also equal to e to the power I theta, which is equal to e to the power I times 60. And then lambda 2, this is equal to 1 over 2 minus I times square root of 3 over 2. And this is e to the power I minus 60. So it looks like the matrix A rotates on average any vector by an angle of 60 and this one is also hidden or written somehow also in the value of the eigenvalue. Okay, the eigenvalue is a complex number. We know that complex numbers, what they can do in a very good way is being able to provide a rotation by an angle of 60. So here we see once again an equivalence between the complex number and the rotational matrix. So in fact, this matrix A, this is a rotation. It is clearly, it's not a pure rotation because it changes also the magnitude. So this is a small problem. So this is a rotation matrix, but not a purely rotational matrix. Purely rotational matrix, there are matrices which look like this, and you know this one, which is cosine theta minus sine theta and cosine theta. So this is a pure rotational matrix, and the A over there, it is slightly different from this for sure. And yeah, I'm trying to think of a possible decomposition of the matrix A. Okay. Yeah. Okay. So this is what I wanted to make clear for all of us here. And so for what we did so far, do we have any question? Okay. Let me think for a moment. Yeah. We did the complex numbers. Now, okay, then we can have another break here.